Lecture 7 Slope and Deflection. Slope at any section of a beam is the angle which the tangent at the section makes with the horizontal. Slope at any section of a beam is the angle which the tangent at section makes with the horizontal. It is denoted by theta. Take this is beam, unloaded beam. There is no load on this beam. There is no load. When loaded, just like this is a curve. This is an elastic curve. This bends like this. This load bends this beam like this. Beam loaded with point load at this point. This is neutral axis. Neutral axis. This is tangent at A. Tangent at A. Tangent at A. This is A. A. This is B. This is tangent at B. Slope at any section of a beam is the angle which the tangent at section makes with the horizontal. Tangent at this section makes with this horizontal. This is neutral axis. This is theta A. Theta A. This is theta B. Theta B. This is tangent at this section, and this is horizontal. This is neutral axis. This is slope. Deflection. Deflection at any point on a beam is the vertical distance between the elastic curve of the loaded beam and the neutral axis of the unloaded beam. Deflection at any point on a beam is the vertical distance between the elastic curve of the loaded beam and the neutral axis of the unloaded beam. This is elastic curve. Elastic curve. This is elastic curve. When this beam is bent like this. This is neutral axis. Original beam. Horizontal or neutral axis. This is deflection at point B. At point C. Take this as C. This as C. This is a point between neutral axis and the curve. Point on the curve. The distance between the point on the curve and the neutral axis is called deflection. Methods of finding slope and deflection. These are various methods for finding slope and deflection. Important methods are moment area method, double integration method, macularis method or singularity method, conjugate beam method, virtual work method, the like. Moment area method. This is moment area method, double integration method, maculari or singularity method, conjugate beam method, and the virtual work method. Take moment area method. Determination of maximum slope and deflection by moment area method. Take simply supported beam carrying a point load at the mid-span. Carrying a load at mid-span. This is simply supported beam. This load is symmetrical. This is L over 2. This is L over 2. This is L over 2. It's total L. Symmetrical load. Then, when we calculate this, X, this is RA times L minus W times L over 2, we get W over 2. Then this is W over 2 plus W over 2, this is W. Calculate bending moment diagram. This is W over 2 times L over 2, WL over 4. This is bending moment. From this, W over 2 times L over 2, this is WL over 4. This is bending moment diagram. This is centroid from B. Centroid from B. This is centroid from B. At midspan, neutral axis is this axis is tangent to this point. Slope at this point is 0 because slope is the difference between tangent at section from neutral axis or from horizontal. This is horizontal. This is the same as this parallel to this. From this tangent to this tangent, from this tangent to this horizontal is 0. Means that this horizontal is tangent at this point. This horizontal and also this is tangent at this point. From this tangent to this tangent, this is 0. There is no angle. 0 angle. No slope. Slope at this point is maximum. Deflection at this point is there is no deflection at this point, and at this point simply supported beam. No deflection. Deflection at this point is maximum, but we calculate deflection at this point by calculating deflection at this point. Means that the tangential difference between B and tangent at D. This is take at D. Take this at D point. This is tangent at this section and the tangent at this section. The tangential difference between this is deflection of B relative to D. But this deflection B relative to D is equal with this deflection. When we calculate relative deflection of B relative to D, we get deflection of D. It is equal. So we calculate deflection of B relative to D by calculating area between D and B, multiplying this by centroid from B to this point. Since the load is symmetrically placed, the slope of the beam at the centroid is 0. C or D is 0. The slope will be maximum at the ends. The deflection will be maximum at the center. Area of bending moment diagram between B and the C is WL over 4 times L over 2 times 1 over 2. This is WL square over 16. This is W L over 4 times L over 2 times this is centroid of this is area of this is first area WL over 4 times L over 2 times 1 over 2 because it is triangle. WL over 4 times L over 2 is area of this times 1 over 2, this since it is triangle. This is WL over 4 times L over 2, this is L over 2, this is L over 2 from this is L over 2 times 1 over 2. This is area of this. It is slope at this point. This area is slope at this point. Distance of central gravity between from B is 2 over 3 of L over 2. This is distance from this to this is 2L over 2, 2 over 3 of L over 2. From this to this is 1 over 3 of L over 2. This is L over 2, total is L over 2. So this is 2L over 2, 2 over 3 of L over 2 times area of this. We calculate deflection at this point or relative deflection of B relative to D. This is distance of the gravity. Theta maximum is slope, that is A over EI, WL square over 16. y maximum deflection on y maximum is equals to a x centroid WL over 4 over 16 times L over 3. This is L over 3. 2 over 3 of L over 2 is L over 3. Times this, it is y deflection, y maximum. Y maximum is WL cubed over 48 EI. Simply supported beam carrying uniformly distributed load. This is uniformly distributed load on simply supported beam. When we calculate moment diagram, this is W. This is WL. We calculate this times W times L. This WL is the load concentrated at center. This is where we calculate simple distributed load multiplying by length, then it is concentrated at this point, WL. WL is divided into 2. This is WL over 2, WL over 2, WL over 2, WL over 2. But the bending moment is WL square over 8. It is when we calculate bending moment diagram, calculate like this: WL square over 8 at center. Then this is elastic curve. This is elastic curve. This is tangential difference between, this is D, take tangential difference between P and the D. Just like we calculate the simply supported. The shape of bending moment is parabolic. Area of bending moment diagram between B and C. Area WL square over 8 times L over 2 times 2 over 3. When we calculate area of parabolic section, we multiply by 2 over 3. For example, when we calculate area of this total, WL square over 8 times L times 2 over 3. We calculate by 2 over 3. But now we calculate half section. This is WL square over 8 times L over 2 times 2 over 3 of this area of parabolic section. Distance of central gravity of area BCD from B is, it is a formula, it is 5 over 8 of L over 2. For this, from this to this is 5 over 8. Centroid 5 over 8 of L over 2. 5 over 8 of L over 2. This is formula to find centroid from parabolic or parabolic diagram. 5 over 8 of L over 2. This is centroid from B. Theta maximum slope at A and B is area over EI. WL cubed over 24 EI. We calculate already. Because this is the slope of bending moment diagram is parabolic. Area of bending moment diagram is WL square over 8 times L over 2 times L over 2 times 2 over 3 of L over 2. 2 over 3 of this is area of this parabolic. This is slope. WL square over 24 EI. Slope of this. This is slope of parabolic section. This is y maximum deflection is x bar is 5L over 16. 5L over 16 times area of this is deflection. This is 5 WL to the power of 4 over 384 EI. Thank you for today.